So today we move to problem number 7 of the 2025 California Institute of Technology Math Meet. This is the Caltech version of the integration B. The problem in the hard series, the final was the definite integral from x equals to 0 to x tending to infinity of e to the power negative x squared times cosine 2x. So this is an interesting problem, and we're going to see how to solve this problem. Um, so I hope you hang around before we proceed. If you haven't subscribed to our channel, we do encourage you to subscribe to our channel. If you please share our videos to some of your colleagues just to increase this community. Here at Everyday Mathematics, what we do is we do like looking at harder problems and see ways we can solve them and share with you. So I hope you hang in tight and let's see how maybe we'll solve this problem. So here we're going to use what we call the Leibniz integral rule. And this is obviously popularly known as the Feynman technique, or some people would call it differentiation under the integral sign. So for integration here, we would choose this 2 here to be the parameter such that if we look at this integral in totality, it's a unique example where 2 is a parameter, such that I2 is our integral in question, but a more general integral would have this position take another parameter such as beta. But let's first of all look at what Leibniz integral rule is all about. It tells us that when you differentiate an integration or an integral, um, it's and this integral here has limits ax, lower limit ax and upper limit bx, such that the integrand is also fxt, and we're integrating in with respect to t. If we differentiate with respect to x, then this is what we get. Now, notice if bx and ax are constants, then this initial two terms collapse to 0. So we're just left with an integral of the partial derivative of the integrand with respect to x. So obviously the guy who really brought more attention to this technique is Feynman. And Feynman was a professor at Caltech, previously at Cornell, but obviously much of his adventure reported in his book, Surely You're Joking, Mr. Feynman, talks about his experience at MIT and Princeton. So let's go back to our integral. If we say this integral is I beta, such that is the integral from x equals 0 to x into infinity of e to the power negative x squared of cosine bx, beta x, sorry, um, then we differentiate with respect to beta, then this is the same as since 0 and infinity are these constants, the same as the integral of the partial derivative of e to the power negative x squared cosine beta x with respect to beta, obviously. Now, since this e to the power negative x squared has no beta term, it's the same as the integral from x equals 0 to the x tending to infinity of e to the power negative x squared times the partial derivative with respect to beta of cosine beta x. That derivative is negative x sine beta x. And what we can now see is that negative x e to the power negative x squared is the same as the derivative with respect to x of half times e to the power negative x squared times now sine beta x. So this is our integrand, and this representation here is certainly ripe for the use of what? Of partial derivatives or integration by parts. Rather. So let's go on and see how we can do that. As we had said, that this is obviously what we have, and now we can say how do we integrate this using integration by parts. Now, integration by part tells us that if you have an integral of a product of a function v and the derivative of a function u, and as we can see here, function u could be taken to be as half e to the power negative x squared, and that v to be sine beta x. The answer for that would be the product of u and v minus the integral of the product of the function u times the derivative of function v. So that taken into account, the product of u and v is half e to the power negative x squared times sine beta x. Obviously, the limits now take into consideration minus the integral of u, which is a half e to the power negative x squared times the derivative of sine beta x. So what do we do next? The derivative of sine beta x is with respect to x is beta cosine beta x, and now that times this I have, so here we have beta over 2 times e to the power negative x squared cosine beta x. So let's try to evaluate what we have here initially. Limit as x tends to infinity of half e to the power negative x squared sine beta x. Since sine beta x oscillates between -1 and +1, what we have here is that as x tends to infinity, half times e to the power negative x squared tends to 0. So the product of 0 and this oscillation here just tends to 0. Minus, as x tends to 0, this part here tends to half e to the power, half times e to the power 0, which is just half times 1, but sine beta x will tend to 0. So this part also tends to 0. So what we're left with is that the derivative of our integral I with respect to beta is just the same as negative beta over 2 times, and then we see, oh, this integral here is our initial integral, which is I. So the derivative of I with respect to beta is the same as negative beta over 2I. Obviously, this is 0 minus 0, so we've indicated here accordingly. Okay, so our problem has brought us here, and we can just simplify it in a very succinct fashion. So we have a differential equation, and now we can separate on one side the i's and on the other side beta. So we have now di over I is equals to negative beta over 2 dB. So when we integrate both sides, this is a famous integral. We have natural logarithm of I being equal to negative beta squared over 4 plus a integration constant c. So taking raising everything to the power e, so we have I to the power I on the left hand side being equal to e to the power negative beta squared over 4 times e to the power c. So this e to the power c is just a constant. We can represent that as a constant 1, c1 rather. So we have I of beta being equal to e to the power negative beta squared over 4 times a constant c1. So what happens if beta is taken to be 0? When beta is taken to be 0, that is equal to our constant c1. So we need to really evaluate what c1 is all about. So plugging 0 to our original integral, cosine beta x becomes 1. So we have half the Gaussian integral, which is root of pi over 2. So c1 is root of pi over 2. So what we can do now, we can say, okay, I beta was equal to e to the power negative beta squared over 4 times c1. We found c1 to be equal to root pi over 2. So I beta is root pi over 2 times e to the power negative beta squared over 4. But our original integral has beta being 2. So we substitute for 2 in place of beta, and so I of 2 is equals to root pi over 2 times e to the power negative 2 squared over 4. Negative 2 squared over 4 means that that is negative 4 over 4, which is negative 1, right? So our last step here shows us that the answer to our problem here is root pi over 2e. And obviously this e here comes here because e to the power negative 1 is 1 over e. So that is the answer that was being sought for. Again, just a quick reminder to our subscribers, thank you so much. We don't take your support for granted. Please keep watching. Don't skip any ads. Share if you can. Let's grow this community. We'll continue looking for these very interesting problems. That is a promise we'll hold on our end and sharing with you. So until next time, tutaluka la prochaine fois. Have a great time and see you. Ta-da!